Okay, lesson 71 is our first solids of revolution lesson. Okay, so solids of revolution. We are going to be looking at how to find volume. Basically, when we take, normally if we're doing area under a curve, right, you're doing the integral of the curve, and that's finding the area between the curve and the axis, right? Well, now the idea is, so that's a flat surface. Now the idea is we're going to take that flat surface, like whatever that shape of that area is, and we're going to take it and we're going to spin it around an axis. So we're either going to take it and spin it around the y-axis, or take it and spin it around the x-axis and have a three-dimensional shape down. And that three-dimensional shape is what we're going to be finding the volume of. Okay, so it's going to be our calculus way of finding volume. Okay? And that's what I was trying to, what you heard is I was trying to see if there's a good video. And most of the videos go with the later on methods, like when we talk disk method and some of those. And so I was looking to see if there's a good method, but we'll go with what we have right here and see. I'll throw a video in at some point, just maybe not today. No. Yep. Okay, so we're going to take a region bounded by two values still, A and B. We're going to spin it around the axis of revolution. So could be the x-axis, could be the y-axis. Eventually it could be some random line like x equals 2 or y equals 3, but that's down the road. Okay? Right now we're just spinning it around either the x or y-axis. Okay? The idea to find the volume is that you cut a slice off of it, lay it flat, and basically we're kind of finding the area of that slice. Okay, so cut a slice off of the solid, lay it flat. The radius of that slice will be equal to the function. Okay, and so thus, when we start talking about volume, the volume of the solid is always going to be this format right here. This is when we're just rotating around a basic axis. It's the integral from a to b of pi times f of x squared dx. So first of all, notice f of x. That f of x will be squared. And they just point out over here that the radius will be equal to the function. So whatever our function in question is going to be equivalent to the radius. Does pi r squared mean something to you?
Yes.
Pi r squared is area of a circle. Pi r squared, area of a circle. Know it. Okay? So pi r squared is area of the circle because the idea, when we rotate something around the x or y axis, it's going to form a circle. So when we cut that slice that's a circle, you're doing the pi r squared. Okay, so this is the format for finding the volume we're going to use. Let's look at example 1 and work with setting this up. Find the volume. So keyword. You see the word volume, yes? Not just talking area, but volume. Of the solid of revolution formed by revolving the region bounded by y equals negative x plus 1 and the coordinate axes around the x-axis. So we're given this y equals negative x plus 1. It says and the coordinate axis. And we're going to revolve it around the x-axis. You have to watch what axis they say, because that can vary from problem to problem. So, can we look at a picture first, please? What is y equals negative x plus 1? Okay, so it has a y-intercept of 1, slope of negative 1. And notice it specifically said bounded by this and the coordinate axes. So the coordinate axes being the x-axis and y-axis. we just talked about, has a y-intercept of 1. So it's going to go through right there. And then what's the slope of negative go? Down 1, over 1?
Is that 1 to the left? 1 right? Is it? Okay.
Sorry.
It stopped. Okay. I just wanted to make sure.
Nope, good question. I didn't realize it was off the screen. Is that better?
Yes.
Does it make sense what I've drawn up to this point? XY axis, I put my y-intercept as 1. I went down 1 over 1. So now I can draw my line, yes? Okay, so let's get everyone here. The region we're talking about is bounded by this diagonal line and the coordinate axis. So the region we're talking about is that right there. Now, if we're finding area, we'd just be done there. We could integrate. But this wants volume as we revolve this around the x-axis. So that means what we're going to do is we're going to take this triangular shape and we're going to revolve it around the x-axis. I always draw that little swirly thing. It just reminds me which axis am I revolving around, because that will not always be the same.
So we're going to draw again.
No, we're not going to draw it, because what's happening is that, so right there it's a triangle, yes? If we take that and we rotate it 360 degrees around that axis, try and visualize what shape is happening.
Same radius on the bottom.
It's keeping the same shape. This is where maybe I should have found a video. I ran out. So right here, it's a triangle right here, yes? Okay, and then what's happening is this line right here is going out and around. And so then as it comes back down here, pretend that's equivalent. But this whole thing, it's three-dimensional. It's making a three-dimensional shape all the way around.
As the axis.
Okay. My video, since I started it and it played before lunch.
Is this what was talking?
Yes, but it just keeps talking through. It just keeps going to the next video, the next video, the next video. Which is, yeah, I know. It just kept going to the next video, the next video, the next video. I don't know. Let's see if this one. Okay, so this is a square root of x graph. And we haven't talked about this yet, but they're talking about, like, cutting a strip. I don't know if this one's going to be a good visual or not. Yeah, I'm not sure this is not. I just wanted a basic video. I don't like what this one's doing. It says it's disk method, but... I wonder if this is the one I started off with earlier.
Are you messing up your recording now?
My recording is picking up all that I'm saying. It's just showing what's on the Elmo. Okay, so this is not going to be great, but let's see if it'll show. Watch here, the y equals square root of x. Okay, they have two graphs going, and this is why I didn't want this video, but actually, I take that back. They have three. But watch this. They're going to take that section right there, and they're going to rotate it. There's the three-dimensional shape. Now, ours won't have a hole in it because we're not to that yet. And then what's happening is they're pulling out that section, and we're finding the area of that circle. And then when we integrate it, that's going to represent the volume.
That's not what I was picturing at all.
Yeah,
Okay.
I was going around the clock.
So can you see how this is going to essentially form, as Jack called it earlier, I can't draw a cone. But our triangle right here is going to form a cone.
Oh, yeah. Okay.
Okay, so there's one without a hole in the middle.
That makes sense.
It looks
If
like the
only ours just like split, it'd be the same.
Yeah.
Enjoying
And ours is straight instead of curved, like that one. Okay, does that help for a visual then?
Yes.
I'm sorry, I can't draw it. I mean,
Actually, can we copy down the link?
honestly, if you just search, like if you just get on and search like disk method, like solids of revolution disk method, you can find a lot of different things. You really can. So the idea here then is, I guess, we draw this. You know, you're going to have the cone right there. Are we kind of there?
Yeah.
Okay.
At first, I was really just trying to figure out how to
That's
make
right.
colors.
Okay. But you can visualize now that you've seen some. Okay. Okay. That was what I was trying for. Now, we're going to have voices later if I don't pause this.
I mean, it's not really confusing. It's just they're rotating around that certain axis. They just add a Z.
Okay. So, back to this at hand. We have this triangle. It's going to rotate and form a cone now, right? So we're essentially finding the volume of a cone. But we don't have to know the volume formula or anything. What's going to happen is that we're going to take a slice of this. Okay, so if I take a slice of this right here, okay, and since I'm rotating around the x-axis, my slice is perpendicular to the x-axis. And this represents dx or delta x, as in, you guys remember delta x being the change in x? And so that little slice represents the change in x. Now, the idea is there's multiple discs piled on top of each other. Like you saw in that first video with the colors, there's multiple discs piled on top of each other. We're just doing one representative disc, and then we do the integral from whatever a to b is. It's doing all the discs together. Okay? So, I'll write down cone here, that this was a cone example. And this line was y equals negative x plus 1. I think I have everything relatively labeled there. Okay, so my integral, first of all, is always going to start with a pi times. Okay, it's the radius squared. However, the radius of this cone is the same as the distance from the x-axis to our line, our graph. And so that graph, our graph is our radius. So f of x, or in other words, y equals negative x plus 1, is our radius. It's kind of the idea, you guys know when we did area, we did upper minus lower. But before we did upper minus lower, we just did integral of the upper. That's kind of what we're doing today. When we get to Washer method, we'll talk upper minus lower, or a variation of it. But right now, it's always just going to form a solid thing. So we're going to do pi times the function squared, so negative x plus 1 squared, times dx, which represents the change in x, or it represents the width of one of those little discs. Okay? Now, the question is, what are my a and b values?
0 to 1.
Why 0 to 1?
That's the part where it stops at the coordinate axis.
Okay. If we were doing the area under the integral, we would have 0 to 1. Yes? Okay. So no, it's the same idea here. Because we're rotating around the x-axis, it is this 0 to 1 right here. If we were going around the y-axis, it would happen to also be 0 to 1, but it would be this 0 to 1, because we would have to be in terms of y. If you rotate around the x-axis, you're in terms of x. If you rotate around the y-axis, you're in terms of y.
A and B are dependent on axis.
Yes. Okay. And we've got it set up. Okay. That pi, what can I do with that pi?
Move it out front.
The pi is a constant. It can go out front, so it's the pi times the integral from 0 to 1. Officially, what do I need to do with negative x plus 1? If it's negative x plus 1 squared, FOIL it to square it, because this is one that we can do without a calculator. So if we FOIL this, negative x times negative x is x squared. Outside and inside, minus 1x makes it minus 2x plus 1 dx. We need to keep practicing this by hand because these have been rough on tests, guys. So my pi carries down. It's an integral. That means my powers are going up. What's the integral of x squared?
1/3 x cubed.
Are we okay with that? Add 1 to the power and divide by the new power. Minus integral of 2x. Add 1 to the power, divide by the new power. X squared. Plus integral of 1. X. When it's a constant, you always just add it on. And then we are evaluating from 0 to 1. My pi, again, I'm going to leave out front. Fundamental theorem of calculus says we're going to put 1 in and then subtract what we get when we put in 0. So when we put 1 in, 1/3 minus 1 plus 1 minus, what about when we put in 0?
It's going to be straight 0.
0 minus 0 plus 0. Well, enjoy the easy problem here. Ends up being 1/3 times pi, so pi over 3. Since this is volume, my official label can be questions there.
Yeah.
Okay,
So is that the volume of just the disk, or is that the volume of the whole shape?
the whole shape.
Okay.
By integrating from 0 to 1, it makes it the whole shape.
But if you use the start and stop of the disk, it would be just the disk.
Right.
Okay.
Okay, ready for example 2? Find the volume of the solid formed by revolving about the, what? X-axis. Just pointing it out. Region bounded by the graphs, y equals e to the x equals 0, x equals 1, and the x-axis. There's 4 pieces, but basically it's the graph and then they're telling you the 3 boundaries.
It's not three.
No. It's not scary, I promise.
It sounds scary.
It would be scary if we had other, like, besides y equals e to the x, if we had other, like, x functions. But these x equals 0, x equals 1, and x equals, or in the x-axis are all just horizontal vertical lines. Okay. Yep. They're helping you with the boundaries. So here's x and y. Sure. I just need the reminder. We're already told we're rotating about the x-axis. What does y equals e to the x look like?
It's the exponential function. It starts at 1 on 0.
Yeah. The exponential function over here on the left would be running along the x-axis. When it hits the y-axis, it's going to cross through 0, 1. So that's good to know right there that that is 1. So that's y equals e to the x. X equals 0. What's x equals 0? The y-axis. What's x equals 1? The vertical line, x equals 1. And what's the x-axis? The bottom boundary. So, have you visualized the shape here?
Weird slant.
So that's what we're rotating. When we rotate that around the x-axis, you have to think three-dimensional. So, I don't know that I could draw. I mean,
Kind of like a funnel, but strange.
with something like that. Huh?
Looks like a little pop.
So the bottom's always going to be round.
Well, that's just how I draw the picture.
Because in my head, I was picturing a square. Like a square bottom. But I guess it's rotating.
It's always going to be circular because we're rotating around something.
That'd be a weird shape.
Exactly, it is. It is a weird shape. I'm not going to argue that at all.
I think that's why I initially thought like a square.
So, okay. Now, the important part of this. There you go. Integral. Now, keep in mind I did draw it in, and I should be in the habit of drawing it in. The rectangle is going to be perpendicular to the x-axis, right? That's what we are rotating around. That represents one disk. And you can think of that as being dx or delta x. Okay? Okay, so what are you putting in here?
Pi times e to the x dx.
Okay. Always pi. The function squared, which is e to the x squared. You didn't say the squared, did you?
Not it.
I didn't even catch that yet. And then always times a dx. What about my boundaries here?
0 and 1.
0 and 1 again? And it's one of those, we haven't hit a good boundary one to really test what you understand there, but it's at 0 to 1 along the x-axis. So I can take my pi and pull it out front, the integral from 0 to 1. What is e to the x quantity squared? What do you do with a power raised to a power?
Did you multiply it?
You multiply. When you have a power raised to a power, you multiply. So this is really e to the,
X squared.
no, 2x. Not, we're not raising a power to a power. We're multiplying. Okay? Questions to that point? Okay. I'm going to keep pi. Okay, think carefully here. We've done this. You know how to do this. Integral of e to some power.
That's the same times chain. Or no. Same times reverse chain.
You have to reverse it. Okay, so the derivative or integral of e to the 2x is still e to the 2x, right? If we're doing the derivative, we would then have to do times the derivative of 2x. And the derivative of 2x would be, well, hold on, listen to my question. The derivative of 2x would be 2. We have to compensate for that 2 when we're doing the integral. So what's going to compensate for a 2? That's the 1/2. Not disagreed, I was just asking a different question. So now the idea is, this is the integral of e to the 2x. If I took the derivative of 1/2 e to the 2x, I should get e to the 2x. Does that make sense? Yes, no? Maybe so. Okay. You just have to think, when I'm integrating, there would be a derivative of 2x in there somewhere. We have to compensate for that 2x. So, okay. Notice the pi I left out front. Technically, if you wanted to, 1/2 is a constant, yes? Mathematically, it'll be easier on us if we take that 1/2 out front. If I take that 1/2 out front with pi, what is pi times 1/2? Pi over 2. and then it's times. So e to the 2x, what do we have to do? Plug in 1 and then plug in 0. So it's going to be e to the second minus e to the 0. So pi over 2, e to the second is just e to the second, minus, what's e to the 0?
1.
Anything raised to 0 power is 1. And we have pi over 2 times e to the second minus 1 units cubed officially. Ready for the next one? Okay, start reading it. Pick out the key pieces. There we go. Find the volume of the solid formed by rotating about the y-axis in the first quadrant region bounded by the line y equals 3, the graph of y equals the square root of x, and the y-axis. Got it? Let's get a graph. Okay. Am I on the screen? I am. I succeeded this one. X-axis, y-axis. Okay, what do we need? Let's get the main one. Y equals square root of x. What's y equals square root of x look like? It's actually the one we saw earlier, wasn't it?
Yeah.
It's the half a parabola. So is that okay? Half the parabola goes through 0, 0, 1, 1, 4, 2, 9, 3. Since I just taught this in Algebra 2. Okay, so that's y equals the square root of x. What else do we have to think about here? Y equals 3. Where is y equals 3? At 3 on the y-axis. So, I don't want to make it too far up or it's not going to work for me. Mine's just going to kind of end up there. So there's y equals 3. This right here was y equals the square root of x. What else did it say? The first quadrant region bounded by the line y equals 3, the graph of y equals the square root of x, and the y-axis. What's my section I'm talking about here?
The top of that weird looking ramp.
Okay. The part is between the graph and y equals 3. So it's actually above the y equals square root of x graph, isn't it? And important to notice, this time we're rotating around the y-axis. Okay? So, I'm trying to think how to describe this funky shape, but if you think about it, so now, this y equals square root of x, it's coming around here, yes?
Is it just going to be like an upside down, really, really pointy triangle with a round bottom?
Cone. Really pointy cone?
Yeah.
Like it will kind of,
It's kind of like a ramp.
It's kind of shaped like
I mean, it is. I mean, there's a three-dimensional quality there.
Yeah.
You know, so it's, the space is going to be a circle. So a cone standing on its tip, but these are going to kind of be curved in. I wish I was a better artist for this lesson, because. Okay. Now, because we're rotating about the y-axis, everything we do on this problem is in terms of y. everything, including your equation needs to be in terms of y. It'll be dy instead of dx. And here's another thing I need to think about. Our rectangle in the past, we were going around the x-axis, so it was perpendicular to the x-axis. Now, my rectangle that is rotating around that's going to make the disk is going to be a horizontal because it's now perpendicular to the y-axis. So this right here is dy or delta y because it's perpendicular to the y-axis. My boundaries are on the y-axis, 0 to 3. What's my equation I'm going to use?
So it needs to be x equals y. So x equals y squared. You'd use 3 minus y squared, since here 3 is on top.
Well, we don't have to, no, we're going around, that would be if we'd be going around the x-axis. We're not going to subtract anything today. We're going around the y-axis. It's flat along the y-axis, so we're good there. But here's the deal, guys. Wade's giving me all these things in y, and then he says square root of x. You see what I'm talking about here? Everything is in terms of y. So before we get started, instead of this equation being y equals, it needs to be x equals. How do you get rid of the square root on the x? Square it. And so this is equivalent to saying x equals y squared. Are we okay with that? So instead of using the square root of x, we're going to use y squared. Everything else I liked you guys were saying. So the integral from 0 to 3, and here's my reminder, those 0 and 3 are what? Those are y values. So from 0 to 3 of pi, the function squared, but it's the function in terms of y. So y squared dy. We got the setup down. So if I pull that pi out front, it's pi times the integral from 0 to 3. What's y squared squared? Y to the 4th dy. So pi times integral of y to the 4th. Add 1 to the power, divide by your new power. So 1/5 y to the 5th evaluated from 0 to 3. I've got the pi. I've got the 1/5. I personally would put the pi and the 1/5 together and make that pi over 5. Y to the 5th is going to be 3 to the 5th minus 0 to the 5th. You do 3 to the 5th. Yep. 243 minus 0 is still 243. So 243 times pi over 5 means I'm going to write this as 243 pi over 5 units cubed. I'm going to stress, you've got to get a good grasp on these because eventually we'll move past this. I mean, not right away tomorrow, right? We'll wait some lessons. We'll move past this and we'll have disk method and I don't do shell method. We'll have displaced axis. Which, by the way, what time? Okay. All of a sudden I looked at the clock and I'm like, okay, wait a minute. I have no idea what time we get out of here. I did hear the first bell. I heard the bell, so I knew we were in the second half of class, which is why the clock really confused me. Okay, let's try another one. Find the volume of the solid formed by rotating about the y-axis. The first quadrant region of the circle whose equation is x squared plus y squared equals 9. X squared plus y squared equals 9 is a circle centered at 0, 0 with a radius of what? 3. Right? This is a circle centered at 0, 0, radius of 3. They specifically said the first quadrant region. So you don't have to draw the whole circle. We're drawing what portion of a circle? Quarter of a circle? Okay, so we've got a quarter of a circle. If it has that was horrible, a radius of 3, it's going to count 3 over and 3 up. Yes? We're rotating about the y-axis. And it's the solid form by rotating, it's in this circle. So what am I coloring in here? It's that right there. So when I rotate this around the half circle, the top half of a circle, an igloo, huh? Yeah. It's basically take a circle and cut it in half. Or wait, bad word, not circle, sphere.
Oh no, we can't.
I was picturing the same thing.
Okay, well that's, in my brain I was too, but I thought, oh no, I used the wrong word. Take a ball, take a basketball, slice it in half.
Okay.
Half of a basketball. Okay? Just don't try and cut a basketball in half with Mr. Bales. I don't think he'll appreciate it.
Didn't look at that.
Okay. So, we're rotating around the y-axis. So our disc that we are rotating, or slice that we're rotating, is perpendicular to the y-axis. Okay? This represents a section of our igloo, of our half of a basketball, of our whatever you want to. And realize those discs are going to get smaller as they get towards the top of the basketball, and they're going to get bigger as they get towards the center of the basketball.
How important is it on the machines where it is just
Anywhere up or down, it just needs to be, in this case, a horizontal disc is the appropriate graphic.
and then it would be vertical for the axis.
Yes. Okay. Now, let's get our equation in order, because right now, x squared plus y squared equals 9. It's not solved for either variable, so that doesn't really help me. Okay, we want this in terms of y, because we're rotating around the y-axis. So, if I solve this for x, it becomes x squared equals 9 minus y squared. So, officially, x is plus or minus the square root of 9 minus y squared. Because officially, when you take the square root in the equation setting, it's plus or minus. But the top half is which half of this? The plus. Got a glare there?
It's like right on top of the x equals. Thank you.
Okay. There you go. The integral of. What do you want me to write down? Got a pi. And I'm going to go ahead and put it inside right now, but you can go ahead and start with it outside. I'll do that at points too. What else? Okay. He says 0 to 3. I'm going to be picky. Which 0 to 3?
A lot.
This 0 to 3 here, yes? And I know that's just me being picky, but I think it's important that you understand which 0 to 3 because they happen to be the same either way. Okay? What else? Okay, so I'm going to write it right now as the square root of 9 minus y squared, but I agree, what are we going to do? We're going to square it. And I agree, Wade, that is going to cancel in a moment. For the purpose of notes, I'm writing the whole thing out, though. And then what do I need to put on the end?
dy.
dy. So yes, what happens when you square a square root? Yeah. So I'm going to pull the pi out front. It's the integral from 0 to 3 of 9 minus y squared dy. And then we're back to just a normal integral. Pi out front. The integral of 9 is 9y minus the integral of y squared. Y third, 1/3 y cubed. Evaluated from 0 to 3. Pi is still out front. Plug in 3. 9 times 3 is 27. Minus 1/3 of 3 cubed. So 1/3 of 27, and 1/3 of 27 is 9. Minus 0 minus 0. So we end up with 27 minus 9 times pi, so 18 pi units cubed. Okay, you're getting the gist. Find the volume of the solid form by rotating about the x-axis, the region bounded above by the circle, whose equation is x squared plus y squared equals k squared, and below by the x-axis. Okay. Now, k represents a constant. It's a number. Okay? So this is just saying that this is a circle, kind of like the one previous, right? But instead of last time it was a circle of radius 3, this time it's a circle of radius k. Okay, so let me draw a picture. X-axis, y-axis. Now, find the volume of the solid form by rotating about the x-axis, the region bounded above, so that's above the x-axis, by the circle, whose equation is x squared plus y squared equals k squared. So we're drawing the region above the x-axis. So we're drawing here. Can't see what I'm drawing again. A half circle. It didn't confine it to quadrant 1 here. It said above the x-axis. Okay? So it specifically said above the x-axis. Now let's put some labels on this. This circle has a radius k. So how far to the right does my circle go? K. How far up on the y-axis does my circle go? K. How far to the left does it go? Negative k officially. If we're looking at the distance. No, k, negative k. Okay. And it wants us to rotate about the x-axis. So
That's what it is.
mm-hmm.
So
Yeah.
now it's just a ball.
It is. Because we have the whole section from negative k to k, you rotate around, it's going to be the whole sphere, the whole basketball, the whole whatever. We get to put our basketball back together now. Okay. So now, integral. What was it? Oh, I thought I heard the boundaries down there. Pi. Okay, now, which boundaries? I guess I never drew my rectangle. We're rotating about the x-axis. So now my rectangle is a vertical rectangle, because we're in terms of x. So this represents dx. My boundaries we're using are x boundaries, so we are going from negative k to k. What is my function?
After you square, it would just be k minus x squared minus 2k. Or now.
K squared minus x squared.
Okay,
Maybe
so
plus or minus, but then you're squaring it. So it doesn't matter.
this one we need in terms of x, so we need solved for y. Agreed? So if you get y squared by itself, it's k squared minus x squared. So officially, it's plus or minus the square root of k squared minus x squared is my actual equation. We only need the top half, so we only need the positive. So officially, it's the square root of k squared minus x squared, quantity squared, times dx. I knew I didn't make it. It would have been fine with this computer, but the laptop's way too sensitive.
Or close.
By the way, I'm kind of offended that you guys didn't say hi to me in the video of the lesson for the next. I would say hi to you guys in your home.
Did you say hi to Aubrey today?
Hi, Aubrey.
Oh,
Oh, now it's different.
See how it is?
Maybe it was because I was upset.
Okay, let's get this problem finished, please. Okay, so pull the pi out front. Pi times integral from negative k to k. When you square the square root, you get k squared minus x squared dx. Carrying down the pi out front. Okay, guys, be careful. The integral of k squared. Remember, k squared is a constant. It's a number. What's the integral of a number?
K squared x.
You add an x, right? So like if I said, what's the integral of 9? You'd say 9x. So what's the integral of k squared? K squared x. Minus. Now, x squared is a normal x. So what's the integral of x squared? 1/3 x cubed. Evaluated from negative k to positive k.
It's a lot of letters.
Welcome to math. You've been doing this for a while. You know it happens. Okay, my pi is going to stay pi. First of all, I'm plugging in positive k. K squared times k, k cubed. Minus 1/3 x cubed is going to be 1/3 k cubed. Minus, new parentheses, now I'm plugging in negative k. So k squared times negative k is going to be negative k cubed minus 1/3 times negative k cubed really becomes plus 1/3 k cubed. Well, in terms of k now, at least. You can do this however you want. If we stay within the parentheses, you've got 1 k cubed minus 1/3 k cubed. 1 minus 1/3 is 2/3 k cubed. Minus, what's negative 1 plus a third. Negative 1 plus a third is going to be negative 2/3 k cubed. So 2/3 minus negative 2/3 is
Why is this
way,
lesson
so I'm looking
so
up at the.
I want to laugh too.
I'm confused now. I just got lost.
okay.
They were adding the 2/3 and the 2/3.
Okay.
Yes, that's what I was trying to get to. I think I went too fast there. My
I think I said
something. I don't know what I did.
okay.
But yeah, 2/3 and 2/3 is 4/3. So we are at 4/3 k cubed, and there's a pi. So I'm actually going to say 4/3 pi k cubed, and that is units cubed.
Would it be the same if you wrote 4/3 k cubed pi?
Yes.
Okay, because that's what I wrote on accident.
Now, if this k was instead an r, what is 4/3 pi r cubed?
What's your volume for a sphere?
Volume for a sphere.
Oh, we just found the volume for a sphere.
We just found the volume for a sphere formula, yes.
On purpose? Is that supposed to be like that, or is that just a coincidence?
It's not, I mean, it's valid. I mean, think about what was this shape going to be? It was going to be a sphere. So we didn't have a radius. Our radius was k. And so, I mean, it came out that way on purpose. It wasn't just, you know. Okay.